Let's delve into the fascinating world of software architecture in embedded systems. Hello everyone, I am Sumaya Kashimu. Today I'll be discussing software architectures in embedded system. This field is crucial because it defines how we structure software components that control hardware operations in devices ranging from household gadgets to complex industrial machinery. Today, we're diving into the fundamental backbone of embedded systems. Embedded software architecture is crucial. It defines the framework for software components and plays a pivotal role in three main areas: reliability, performance, and effective scheduling. First, reliability ensures that the system functions correctly under all conditions. Performance, on the other hand, is about optimizing how fast and efficiently these tasks are executed. Finally, effective scheduling ensures that tasks are managed in a way that balances business needs across various applications. Remember, these architectures are the unsung heroes behind the scenes, enabling everything from consumer electronics to industrial control systems. Now, let's explore specific scheduling methods, starting with simple cyclic scheduling. When discussing about round robin scheduling, we are referring to a straightforward method where each task is given an equal slice of time to execute. This approach has two main advantages: fairness and simplicity. By allocating equal time to each task, every process gets a fair chance to run, and the simplicity of the method makes it easy to implement. However, it's important to note its limitations. Simple cycling scheduling may not be suitable for systems with strict real time requirements. In these cases, the lack of flexibility can lead issues in meeting time constraints. As we move forward, we look into the scheduling which builds upon this concept by introducing a more dynamic approach to task management. Function queue scheduling architectures offers a dynamic way to manage tasks within a system by organizing them into prioritized queues. This method allows the scheduler to efficiently select tasks based on their order or priority, which can greatly enhance systems responsiveness. One of the key advantages of this architecture is its flexibility. By supporting various scheduling policies, it can adapt to different system needs and priorities. This flexibility is particularly beneficial in environments where task demands can change rapidly, requiring a swift and efficient response. Now, let's delve into the crucial role of real time operating system or RTOS in embedded system. First, real-time operating system provides deterministic scheduling. This means tasks are executed in a predictable order, which is essential for meeting the stringent timing requirements of embedded applications. Think of it as having a reliable train schedule where every train arrives and departs exactly on time. Next, we have preemptive scheduling. This allows higher priority tasks to interrupt lower priority ones, ensuring the critical operations receives the necessary attention promptly. It's like giving an ambulance right of way in traffic to ensure it reaches its destination as quickly as possible. Lastly, inter-task communication is another vital component of real-time operating systems. It encompasses various mechanisms that enable tasks to exchange data efficiently. This ensures synchronization and coordination, which are crucial for maintaining system integrity performance, much well like a coordinated team passing a baton in a relay race. Overview of embedded model program modeling. In our discussion on overview of embedded program modeling, we aim to highlight the importance of this process in developing embedded systems. Embedded program modeling acts as a blueprint for crafting predictable and reliable software, which is essential in applications where performance and accuracy are critical. This modeling phase facilitates through testing and verification processes, ensuring that the software functions as intended across its various conditions. There are several key points, like proactive issues identifications. Modeling enables developers to anticipate potential challenges and address them early in the design phase, which can prevent expensive changes later in the development lifecycle. Support for critical testing. Emphasize the role of embedded program modeling in facilitating essential testing. By simulating real world conditions, developers can confirm that the software meets all performance standards and operates correctly in diverse scenarios. Ensuring software correctness. Highlight how modeling contributes to ensure software accuracy. Precise models aid in predicting system behavior, which is especially crucial in applications where failure is not an option. Keep in mind that the aim of embedded program modeling is not solely to produce functional software. It is all about developing robust and dependable systems tailored to meet specific application needs. In these sections, we are focusing on single processor modeling, which is fundamental in the world of embedded system. Let's start by discussing task execution. In single processor systems, tasks are carried out by sequentially. This means each task gets the processor's full attention, ensuring reliability and dedicated resource allocation. Next, we have scheduling considerations. Effective scheduling is essential as it detects task prioritization and management. This balances how response time the system is with how resources are allocated, avoiding potential conflicts and ensuring smooth operation. Now that we have explored single processor system, let's dive into the world of multiprocessor system modeling. In multiprocessor systems, tasks are executed in parallel, which allows us to boost performance and improve responsiveness. This parallel execution can dramatically enhance throughput, making systems more efficient. However, it's important to note that this requires careful resource management and avoid potential issues. One of the key components to focus on is synchronization. Effective synchronization between processors is crucial to prevent data inconsistencies. We use techniques like locks and semaphores to manage concurrent access to shared resources. This helps in avoiding race condition, ensuring that the systems operate smoothly and consistently. As we proceed, we will compare single and multiprocessor systems, highlighting their differences and how each can be leveraged in various applications. As we dive in the comparison between the single and multiprocessor systems, let's spotlight two crucial differences: task execution and communication. Started with task execution, single processor systems operate in a sequential manner. This means tasks are handled one after another, which can be beneficial for maintainability and predictability. However, this predictability comes at the cost of potential bottlenecks, especially during high load situations where multiple tasks compete for the same processor resources. On the other hand, multiple processor systems handle tasks in parallel, allowing multiple tasks to be executed simultaneously across different processors. This setup significantly enhances throughput and performance, but introduces complexity in terms of communication. Effective communication between processors in a multiprocessor system is crucial. This involves extensive interprocessor communication, which ensures all processors are in sync and can work together seamlessly. To prevent data conflicts and ensure data smooth operation, robust synchronization mechanisms like locks and semaphores are essential. Understanding this key differential helps in making informed decisions when modeling systems, whether you aim for the simplicity and predictability of single processor or the performance benefits of a multiprocessor setup. Today we are diving into the embedded software development process, which is a meticulous journey throughout the several critical stages. Each of these stages, like requirements analysis, system design, implementation, testing, and validation, plays a vital role in ensuring the overall reliability and efficiency of the embedded system. First up, requirements analysis is where we lay the groundwork. We gather and analyze what the system needs to do, setting a clear path for future development steps. This stage is crucial as it aligns all the stakeholders with the project's goals and expectations. Next, system design acts as the blueprint for our project. This is where we map out how the system will interact with the different components, establishing a foundation for smooth implementation. In the implementation phase, we bring our design to life. This involves writing the code that will power the system, transforming theoretical plans into practical applications. Testing and validations are our final checkpoints, ensuring that what we have built meets the necessary standards and functions as expected before it hits the market. Each phase is interconnected and contributing to the robust performance of embedded systems. This structured approach allows us to address complexities and deliver reliable, efficient solutions. By understanding and mastering each step, we ensure that our embedded systems are not only effective but also adaptable to future needs. Now we are diving into the core steps of the embedded software development process, emphasizing to the importance of each phase to ensure a successful project. Let's start with the requirement specification. This is the first and arguably the most pivotal stage, where we define the functional and timing needs of the embedded systems. It's crucial to ensure all stakeholders are aligned on the project goals and expectations from the get to go to avoid misunderstandings later on. Next, we move into the architectural design. Here, we select the software approach architectures and technologies that strike a balance between performance and resource constraints and system requirements. This step is all about laying a strong foundation for optimal operation in embedded environments. Testing follows, involving comprehensive processes like unit integration and system testing. These are vital to verify that embedded software functions as intended and to catch any issues before deployment. Lastly, we have coding phase. This is where developers bring the specifications to life, transforming them into actual software applications using the right programming language and tools. Each of these steps is integral to the overall development process, contributing to the reliability, efficiency of the final product. Be sure to keep these phases in mind as we continue through the presentation. As we delve into the development process timeline, let's explore the five critical phases that form the background of embedded software development requirements: analysis, design, coding, testing, and deployment. Each phase plays a pivotal role in ensuring that the software not only meets the initial expectations but also adapts evolving needs through continuous feedback loops. This approach helps maintain software relevance and efficiency throughout its life cycle. It's important to note that these feedback loops are essential for identifying areas for improving and implementing necessary changes, fostering a culture of ongoing enhance and innovation. By following this structure and timeline, teams can deliver robust, efficient, and reliable embedded software solutions that stand the test of time. This is all about my presentation. Thank you all.